Chapter 6 is about momentum. This is the beginning of our second unit. When something has a lot of momentum, we usually think of it as being very hard to stop. The vision I always come up with when I think of momentum is that cartoon snowball that's rolling downhill, that's going faster and faster and getting larger and larger all the time. Okay. Momentum is one of those words that has sort of an everyday usage, but it really means something very specific in physics. Momentum describes basically inertia in motion, but how difficult is it to stop something's motion? The more momentum it is, the harder it is to change its motion. So if we stop and we think, it makes sense that the faster something's going, the harder it is to stop it. If I have two identical cars and one's going 20 miles an hour and the other one's going 70 miles an hour, it's harder to stop that one that's going 70 miles an hour. The other idea is mass. It's harder to stop an 18-wheeler going 20 miles an hour than it is to stop a pickup truck going 20 miles an hour. So both mass and speed seem to factor into momentum. And that's exactly what our definition gives us. Momentum is defined as being the product of the mass times the speed, or the mass times the velocity. Velocity really would be a better word here. The reason velocity is a better word is just like velocity, momentum is a vector. Okay, it has a direction. If I write it symbolically, it looks like this. And the obvious question is always, why did they pick a P for momentum? And the answer is, I don't know. I do know it couldn't be an M, because M equal MV, that'd be very confusing. So momentum is the product of the mass times the velocity. If you want to calculate momentum, it's just strictly multiply. Make sure, let's suppose we want to know the momentum of a 1,000 kilogram car, and it's going 25 meters per second. That comes out to be 25,000. Units are interesting. Some of our units have special names, like newtons, and some don't. Momentum, the units just look like this. Kilograms times meters per second. Notice if you have a 1,000 kilogram car that's at rest, the velocity is 0, it has no momentum. No matter how massive something is, it doesn't have momentum unless it's moving. Okay, so that's momentum. If we want to change something's momentum, well, let's look at momentum and think about it. There's two ways I can change momentum. I can change the object's mass, or I can change the object's velocity. Most of the time, we're not talking about trying to change an object's mass. We don't want pieces of our car to go flying off. We're usually talking about changing the velocity. Okay? We know that if we're going to change momentum, and we're not going to change mass, we're going to change velocity, there has to be an acceleration, right? Changing velocity requires an acceleration. That's what an acceleration is. It's a change in velocity. We know that an acceleration requires a force. The net force equals the mass times the acceleration, or the acceleration is the net force divided by mass. So if I want to change momentum, I probably want to change the velocity, That's going to require an acceleration. An acceleration is going to require a force. All right, let's think about changing the momentum by applying a force. Do I have a good example? Let's just think about something like a baseball. When a pitcher throws the baseball at the batter, if the batter wants to hit a home run, he's going to try to apply really large force. But the other thing he's going to want to do is he's going to want to apply the force as long as he possibly can. Okay? If you think of this cap being the baseball and this marker being the bat, as long as the bat's in contact with the ball, he's applying a force. But as soon as the ball leaves the bat, there's no new force being added. It's just continuing on with inertia at that point. That brings up the idea that not only is the force important, but also the time that you apply the force. Okay? That brings us to the idea of impulse. Impulse. Whoops, this pen's just about gone. Impulse is equal to force times time. Again, if we want to do that symbolically, it would look like this. This gives us the same mystery we had on the previous discussion about momentum. I don't know who decided the symbol for impulse would be a J, but impulse is a force divided over a time interval. Okay? Basically, if I want to have a larger impulse, I want to have a larger force or a larger time interval or both. Okay? The smaller the force, the shorter the time interval, the less of an impulse. Think about that idea of baseball. When a batter bunts, he holds his bat very still so that the ball simply hits it. That minimizes that force and it minimizes that time of contact. So he has a relatively small impulse. He doesn't want to send the ball back over the home. He's not trying to hit a home run. He's trying to actually drop the ball pretty much right in front of him. All right. There's something called the impulse momentum theorem. And it basically says that the impulse, that's Ft, equals the change in momentum. Anytime you see this triangle, that represents a change in something. The impulse, that's force times time, is equal to the change in momentum. Now, if the mass is not changing, a lot of times you see it written like this. Indicating that the impulse is going to be equal to the mass times the change in velocity. Okay, the momentum. If I want a really big change in momentum, and I'm going to erase this bottom one, it's kind of redundant. If I want this to be really large, I want to change that momentum as much as possible. Again, let's go back. I can use the largest force, I can use a larger time, or I can use both. That's really the argument for following through that coaches are always telling athletes, you've got to follow through, you've got to follow through. If you're playing golf, you want to keep your golf club in contact with the golf ball, because as long as they're in contact, you're applying a force. Okay, so you're trying to do it as long as possible, and that's what following through does. Does the same thing in tennis, baseball, soccer. If you're kicking the ball, if you keep your foot in contact with it longer, you will have a greater impulse and resultingly a greater change in momentum. One of the things we want to talk about briefly is bouncing. Bouncing requires greater impulse because there's a greater change in momentum. We just picture something bouncing off the floor. Let's suppose that we drop something, and by the time it hits the floor, it's going, let's suppose it's a 1 kilogram mass. I'm just using some numbers just to think. And it hits the floor, we just drop it, it falls for 1 second. It's going 10 meters per second, okay? So the momentum at this particular time, the momentum is 1 times 10 is 10 kilogram meters per second. But it's actually negative because it's falling. We're going to let signs important with things that are vectors. And so this is a vector quantity, momentum. It's 10 kilogram meters per second, and we can make it negative or we can say down. All right, if it hits the floor and it stops so that it's going 0 when it hits, if I said, what's the change in momentum? Well, it did have a momentum of negative 10, and now it has a momentum of 0. Generally, if you're going to calculate a change, you do the final minus the beginning. So if I do 0 minus negative 10, I realize the change in momentum was 10 kilogram meters per second. So when it hit the floor, if its momentum was 10 kilogram meters per second and now it's 0, if it just falls to the ground and stops, it has a change in momentum equal to 10. But what if it doesn't? What if instead of having a velocity of 0, it hits the floor and it bounces back up and it leaves the floor going positive 10 meters per second? We'll keep it simple. Well, that means it started with a momentum of negative 10 meters per second, and it ended with a momentum of positive 10 meters per second, or 10 kilogram meters. Think of that on a number line. If you were at negative 10 and you end up at positive 10, that's a much bigger change than this one. If you start at negative 10 and end up with 0, that's a change in momentum of 10 kilogram meters per second. But if you start at negative 10 and you end up all the way at positive 10, that's a change in momentum of 20 kilogram meters per second. Bouncing and changing direction always requires a greater impulse. If I redo the math here, and I say, well, the final was positive 10 kilogram meters per second, minus the beginning was negative 10 kilogram meters per second. You can see that change in momentum is 20 kilogram meters per second. That's a bigger change. Or picture it on the number line. If you go from here all the way to here, that's twice as large a change. Okay. If the ball is in contact with the floor for the same amount of time, it generally means there must have been a much greater force imparted to the ball. It's just like, go back to the idea of the baseball player. If the ball is coming at the baseball player at 90 miles an hour and he hits it and he sends it back at 70 miles per hour in the opposite direction, going from 90 miles to 70 miles in the opposite direction is actually a change of 160 miles per hour. Think about that. Positive 90 minus negative 60, that's minus negative 70, that's a change of 160. If it was coming at the batter at 90 miles per hour and he bunts and it just has a velocity of 0, that's just a change of 90. Okay? So anytime something is bouncing, you know that that is a greater impulse, that is a greater change in momentum than if something simply comes to a stop. Okay, I went a little out of order with my slides. But let's talk about decreasing momentum. A lot of times we want to decrease momentum. We need to bring something to a stop. If you have a car, let's go back to this car with a certain amount of momentum. It has a mass of 1,000 kilograms, and it's driving at 25 meters per second. Then it has a momentum of 25,000 kilogram meters per second. And let's suppose you slow down to a stop. Well, when you slow down to a stop, your momentum is 0 kilogram meters per second. So you had to have a change in momentum of 25,000 kilogram meters per second. You decreased, it actually is a negative if you want to be real fussy, because you decreased your momentum by this much. Okay. That doesn't tell us how we decreased our momentum. I'm just saying we had this much and now we don't have any. Well, we know that a change in momentum is equal to the impulse. This change in momentum of 25,000 kilograms meters per second the question is, how do we do it? Well, let's suppose the brakes on your car go out and you don't have the option of just gently braking and coming to a stop. You see up ahead, the road is coming to a dead end. This side there's a brick wall. This side is a big haystack, huge haystack, biggest haystack you've ever seen. What do? Do you drive into the big brick wall and come to a stop? Or do you drive into the haystack and come to a stop? Either way, your final velocity is going to be 0 and your final momentum is going to be 0. So whether or not you hit a brick wall or whether or not you drive into the haystack, your change in momentum is 25,000. You went from 25,000 to 0 either way because you stopped. Well, do I pick a brick wall? Do I pick a haystack? I don't think any of y'all need me to tell you you pick the haystack. Why? The change in momentum is exactly the same with the wall or the haystack. This FT is exactly the same. But the difference is which of these is larger and which of these is smaller. if we run into the haystack, the time it takes to stop is going to be longer. Let's suppose you run into the haystack, it takes you 10 seconds to stop. Well, if it takes you 10 seconds to stop, this force only has to be 2,500 newtons. The haystack gives you a longer stopping time. What if you run into the brick wall? If you run into the brick wall and you stop in 1 second, it probably would be less than 1 second. If I'm going to stop in 1 second, then this force would have to be 25,000 newtons. Got it? 1 second, force is 25,000 newtons. If I can go through the haystack and it takes me 10 seconds, the average force is only 2,500 newtons. Less force means less damage. If you could slow it down where you stopped and it took 100 seconds, it would only take 250 newtons to stop. Okay? So if you want to decrease your momentum, you always have the option of using large forces in very short times or small forces in very long stopping times. The whole purpose in things, safety equipment in cars like airbags, is to slow your stopping time, to lengthen how long it takes you to stop. By stopping more slowly, less force is required. It's the sudden stops. Same thing with a safety net under a trapeze artist. If he falls off the trapeze and he falls in the net, he will eventually come to a stop. But it'll take a longer time and therefore require less force. Like I said, I don't care so much about numbers. I really care that you understand. Let this formula guide your thinking. Same change in momentum. Do I want to do a big force in a small time? Or a small time with a very large force? Well, if that trapeze artist doesn't have that safety net, he's going to stop in a very short time, like the instant he hits the floor, and it's going to be a very large force. Okay? That's the impulse momentum theorem. The impulse is equal, this is impulse, to that change in momentum, or that change in, if you prefer, mass times velocity. Okay. Longer times, less force is needed. Okay, so that's the first kind of big idea in this chapter. We know what momentum is, we know what impulse is, and we know that impulse is equal to the change in momentum. The second big idea is the idea of conservation of momentum. Conservation of momentum comes directly from Newton's third law. Let's think about Newton's third law. We know that it says the force of object A on B is equal to the opposite of the force of object B on A. So, anytime two objects interact, let's suppose we have two things and they collide, they have a collision, they run into each other, there's an interaction there. Whatever force A exerts on B, B exerts the same size force on A. And the length or the time of that interaction has to be exactly the same. One can't be having a force for a split second while this one's having a force for 10 seconds. Remember, this is an interaction between these two objects, and the interaction lasts the same length of time for both of them. So I can put a T here and a T here, and all of a sudden I realize this is impulse. The impulse on object B is equal to the opposite of the impulse on object A. Equal but opposite impulses. that means the change in momentum is also equal but opposite. If B gains momentum, object A loses an equal amount of momentum. That's conservation of momentum. The total amount of momentum stayed the same. It's just like if I was standing here next to my friend and I had $10 and she didn't have any money. Well, if I handed her $5, I'd have $5 less. She'd have $5 more, but the total amount of money didn't change. That's how momentum works, conservation of momentum. If you have an interaction between two objects, that's going to be our system. One object can gain momentum and the other object can lose momentum, but the total amount of momentum is exactly the same as it was before. Now, it's also interesting to remember that momentum is a vector, which means the signs are important. Suppose we have a cannon and a cannonball. They're both at rest. Well, if they're both at rest, the cannonball has 0 momentum and the cannon has 0 momentum. Here, I'll draw a picture. Here's my cannon. Inside here, here's my cannonball. If they're both at rest, the momentum is equal to 0. If the cannon fires the cannonball, not very long cannon I do, and it's leaving this way with a certain amount of momentum, mv, then this has to be going backwards with an equal but opposite amount of momentum. This momentum and this momentum still add up to be 0. Momentum had to be conserved. There was no momentum before. Well, if this gained 100 kilogram meters per second, then this must have lost 100 kilogram meters per second. The momentum would be equal. So, if we say this with words, in the absence of external forces, the momentum of a system remains unchanged. It's important that you know what your system is. If we were talking a minute ago about the cannon and the cannonball, that was our system. The total momentum of the cannon plus the cannonball stayed the same. Now, let's think about it, because sometimes it looks like the law of conservation of momentum is being violated, but it's not. If I drop something, let's just drop a cannonball. If you drop a cannonball, its mass stays the same, but its velocity is changing. In fact, it's gaining momentum. It's going faster and faster. Does that violate the law of conservation of momentum if this is our system? Absolutely not, because there is an external force acting on it. If I let my system only be the cannonball that I dropped, there's an outside force called gravity. The earth is pulling on that cannonball. Okay? In that case, if my system is just a cannonball, it gains momentum. Now, if I make my system the cannonball and the earth, then there's no change in momentum, because any momentum that's gained by the cannonball falling down would be lost by the earth as it moves up to meet the cannonball. Now, We've already talked, we don't ever see that happen. But if I let the cannonball on the earth be my system, then I have conservation of momentum. But if there's an external or an outside force, like here, if I just let the cannonball be my system, then there's an outside force and it's going to gain momentum. Okay? We're going to be looking primarily at situations where there are no outside forces. We're just going to look at a system of two objects, and we're going to see that regardless of the collision or the explosion, collision means they run into each other, and explosion means they fly apart from each other, momentum will be conserved. Okay, now let's talk about collisions first. In the event of a collision, it can be classified as elastic or inelastic. Now, one of the things that always kind of bothered me is if you have elastic collisions, this is things like marbles or pool balls. The objects have to be very, very hard, and they bounce off of each other. In an elastic collision, it says the objects are not deformed, so they can't be bendy or stretchy. They're generally very, very hard. And one of the interesting things is there is no loss of kinetic energy. Well, we haven't talked about kinetic energy yet. That's energy due to motion. So when things are very hard and they collide, they tend to bounce right off of each other, like a bullet ricocheting off of a side of a building or something. Okay, those are elastic collisions. The objects are very hard, and there's no loss of energy. The objects don't get deformed in any way. The other type, which is actually more common, are inelastic collisions. When we have inelastic collisions, the objects are deformed. And we have a loss of kinetic energy. Car wrecks are inelastic collisions. Cars tend to crumple up and stick together, and generally we lose a lot of energy due to motion. Things tend to slow down. I'm not saying things stop. I'm just saying we have a loss of kinetic energy. In these type of collisions, generally what happens is that kinetic energy is converted to heat. Another word for heat is thermal energy. And a little bit of the kinetic energy may also be converted to sound. That's less energy, but you hear collisions. So that takes energy too, okay? So inelastic collisions, the objects tend to be deformed, and there's a definite loss of kinetic energy. In things like marbles and pool balls that are very hard, where they can collide, they don't damage the objects when they hit. Those are elastic collisions. And in elastic collision, we have a minimal or no loss of energy. Let's look at a couple of examples. These are the examples off the slides that are in your PowerPoint. Let me see. I think I have 3 examples for us to look at. In our first example, it says car A is traveling 10 meters per second to the right, and car B is at rest. Both cars have the exact same mass. So car A its mass is equal to m, and its speed is 10 meters per second to the right. Car B, its mass is also equal to m, same exact mass, but it's at rest. It says, if car A runs into car B and they stick together, how fast is the wreckage moving? This is a conservation of energy. We always think the momentum of the system before has to equal the momentum of the system after the collision. So before, so let's just think, momentum before, some will say initial and final, which is the same thing. I can't really calculate momentum because I don't know mass, but that's actually perfectly fine. Before, I have a mass of m going 10 meters per second plus a mass of m going 0. This is car A, this is car B. After, they're stuck together. Well, what is the wreckage weigh? They stick two cars together. It's going to have a mass of 2m. That's its mass now. It has a double the mass. And it's going v. I don't know how large v is. Well, 10 times m is 10m. M times 0 is 0. So before the collision, our total momentum was 10m. After the collision, our total momentum still has to be 10m, conservation of momentum. What does v have to be in order for this to equal 10m? Well, I just can divide, or I can just think. If I just think, how do I make this equal 10m? I probably come up with, oh, well, then v has to equal 5. If I remember my algebra 1, I go, oh, look, I want to get v by itself. Let's just divide by 2m. This is going to be 5 equal v. So you can think about it, but either way, we get that the speed is 5 meters per second. That makes sense. All of the momentum was in this first car. It had a mass of m and it was going 10 meters per second. If all of a sudden it has twice as much mass, it makes sense that it's going to have half as much velocity because the momentum has to stay constant. Okay, let's look at some problems with a big fish and a little fish. If I have a big fish, my big fish has a mass of 5 kilograms, and it's swimming directly towards a little fish. And my big fish is going to go, how fast did I let my big fish go? 3 meters per second. And over here I have a much smaller fish. It has a mass of 1 kilogram, and it's traveling it's also traveling 3 meters per second, but it's traveling in the opposite direction. So this is our system. We need to be really careful when we think about momentum with direction. The question says, after they meet, the big fish, when they run into each other, opens his mouth, swallows the little fish. How fast will they be going? Okay, well, so this is the before, and this is the after. And in his tummy here, Here's our little fish. Okay. Afterwards, how much mass do I have? Well, if a 5 kilogram fish swallows a 1 kilogram fish, I have 6 kilograms. Probably your intuition is good enough to know that I think it will still be moving to the right. But we don't even have to know for sure. We want to know how fast. Well, the momentum before has to equal the momentum after. Before, mass times velocity, 15 times 3. Well, let's just write it down. That's the momentum of the big fish. Plus, the little fish has a mass of 1 kilogram, but this is really important. It has a velocity of -3. Velocity has direction, momentum has direction. This has a momentum of +15, but the little fish has a momentum of -3. The total momentum before the big fish eats the little fish is 12 kilogram meters per second. If somebody makes a goof on this problem, it's going to be because they're going to say, well, this had 15 and this had 3, so the total momentum must be 18. But remember, when vectors point in the opposite direction, it doesn't work like that. We've got 15 to the right, we've got 3 to the left, so our total momentum is only 12. Momentum's a vector. We have to add it like vectors. 15 to the right, 3 to the left is a total of 12. So, after the big fish eats the little fish, the momentum still has to equal 12. So this is going to equal 6 kilograms times V. Again, we don't have to be a math genius to figure out what V is. This is a total of 12. My mass is 6. If I do 12, this has to be 2. So because of conservation of momentum, if nothing else changes, this combined fish, it's like our car wreck, only now it's our combined fish, is going to continue to move 2 meters per second to the right. Okay. I could turn this problem around. Now, if I make my little fish go this way, and let me think for a minute. And I let him, he can't go 3 or the big fish won't catch him. He has to go slower than 3. So let's just let him go 2 meters per second. What's going to happen this time? Will things slow down? Will things speed up? It's a little bit less clear, but let's find out. Here's our little fish after he swallows them. Before, I have 5 times 3 to the right for the big fish, plus 1 times 2 to the right for the little fish. Now, this total momentum is 15. I have 17 kilogram meters per second. There's a kilogram. That's my before. My after momentum is 6 times V. The numbers aren't as easy, but I can tell you that the V is going to equal whatever 17 divided by 6 is. Turns out that that's going to be equal to 2 5/6 or 2 point. Let's do that on the calculator. 17 divided by 6, 2.83. So it did slow him down a little bit when he swallowed that. When he got heavier, he slowed down. Okay. Let's do one example of an explosion where things are both at rest. Let's go back. I think I have an example with that cannonball. We have a cannon and a cannonball, and they're both at rest. And then the 200 kilogram cannon fires a 10 kilogram cannonball at 10 meters per second. All right, before everything was at rest. So we started off with that picture where here's the cannon and here's the cannonball. The total momentum was 0 because we have 200 times 0 plus 10 kilograms going to 0. The whole thing was 0 before. That was our beginning. Afterwards, we have a 200 kilogram cannon going some unknown speed I'm going to call v. But I know what's going to happen. If there's no friction, we're assuming there's no friction, the cannon is going to go this way, and the cannonball is going to go that way. It's going to have what we call a recoil velocity. Just like if you fire a gun, if you've ever shot a rifle, the bullet goes one direction, the rifle goes back into your shoulder. That's that recoil velocity. Okay, plus we do know the momentum for the cannonball. It has a mass of 10 kilograms and a speed of 10. So I have 0 equals 200v plus 100. How is this going to equal 0? Well, the only way it can equal 0 is if v turns out to be negative, which it will. If I rearrange this, if 200v plus 100, if I subtract 100 to the other side, I get 200v has to equal negative 100. In other words, negative 100 plus 100 will come out to be 0. If I do negative 100 divided by 200, I get that v is equal to negative 1/2 meters per second. Or if you used a calculator, you might have gotten a decimal. So you'll notice the recoil is much, much smaller. The reason being, of course, the cannon was much, much heavier. But both of them had change in momentum. The cannonball gained 100 kilogram meters per second. The cannon lost 100 kilogram meters per second of momentum. A negative momentum and a positive momentum can add up to be no momentum. All right, I think that concludes, well, I know it concludes chapter 6. If you have any questions, always email me. Good luck on the homework.